Good afternoon, everybody. I'm Dr. Rajkumar Bondugula, and I'm a data science fellow in the AI Center at Verizon. Today, I want to take a critical look at simple question. Is AutoML a panacea for data science talent shortages? Lately, we have seen a lot of vendors release tools such as AutoML or AutoAI or other tools calling themselves no-code or low-code tools. And the assumption behind these tools is that they will let people without data science background practice data science. In fact, this morning, there was a talk in this conference from a large vendor promoting such software. So in next couple of minutes, let us take a look to examine if data science is really simply building models and coding, or is there something more to it? So first of all, before we go into the characteristics of AutoML and what it can do and what it cannot do, let's take a simple look as to what data science really is. So data science is a contemporary KDD practice. So in this practice, we have raw data and we want to extract insights out of this raw data. And in data science, the raw data comes in many flavors, such as it comes in large volumes, it comes in many varieties, it comes at a high velocity, and it comes in a variety of veracities. That is, the truthfulness of this data varies, and also it also comes in variety of values. So not all data is equally important. Then this raw data is processed using a variety of technologies and is input into a data mining platform that typically is a distributed computing platform and a distributed storage platform, mainly to accommodate for the complexity, for the size complexity of the data that we're using. So once the interesting patterns are identified, then post-processing is applied and insights are extracted. So if the insights are ready to be productionized, then the process stops, the science stops, and the engineering begins. So what we want is now what a data scientist has converted the raw data to insights, and we want to automate that process and repeat that process on a regular basis. So data science is a practice that is concerned with extracting generalizable insights from data. And it's the art of examining reality in the light of observed data. So now that we have a broad sense of what data science is really about, let's take a closer look at when and where does AutoML fully live up to its promise. Suppose in your organization, most of the problems have certain characteristics, then AutoML really works for you. For example, the problems are easy to formulate. What I mean by that one is, more often than not, when business comes to you with a certain problem, it's not very clear as to how the problem should be formulated. So let's say, for example, fraud. Can we formulate fraud as a classification problem, or should it be formulated as an anomaly problem? But in your case, if you're lucky that your problems are easy to formulate, so one of the conditions necessary for AutoML to work is already met. And once the problem is formulated, the next immediate thing that the data scientist has to worry about is labeled data availability. More often than not, labeled data is neither clean nor available. So let's say in your case, you're somehow lucky and you actually have labeled data. And the third thing is that the desired classes are clearly separated. So you have a problem where humans agree of what the output should be. So that means the desired classes are very clearly separated. And if human beings are able to do, there is a chance that machines will be able to do an equally good job. Okay, so let's say if that condition is also met, then the final one, then like the last two conditions, right? So many times AutoML, it goes to the data, it builds a model, it fine tunes it, but even after fine tuning, it has certain performance characteristics, precision, recall, accuracy. And if you are okay living with that kind of precision recall characteristics, then you're okay. Then AutoML might work for you. And finally, lately, many large software vendors are releasing pre-trained deep neural networks. And if your problem can be formulated in a similar way, then you are in luck. Or in other words, the more characteristics you have, the more likely AutoML will work for you. Not only that one, if you look into the flow of a typical data science practice, AutoML is a very good sweet spot in the data mining aspect of the KDD practice, in the data mining aspect of the data science aspect practice. So let's say you've already decided that your problem is a classification problem. So you have a bunch of choices. So what you tell your AutoML software is, here is my data and I need you to classify, here are my classes. Then AutoML can very quickly go through, cycle through a couple of models, and it will very quickly be able to tell you, you know what, decision tree is perfect for you. Okay. Or sometimes, even if you say, for example, let's say if you decided that you want to use a neural network, then you still have to try out many things, such as different variations of the neural network architecture, such as increase different number of hidden neurons, different number of hidden layers, and different number of hidden neurons in different layer, different kinds of regularizations that you want to apply, and different activation functions that you want to use for those neurons. So for those aggregating neurons. So there are several decisions that you need to make, and there is no real analytical way of telling what combination actually works for your data. So therefore, AutoML is fantastic here. It can try out pretty much all of these combinations pretty much in automated fashion and give you a configuration that actually works really well for you. So overall, if AutoML somehow fits your situation, it's really good, because the cycle time is greatly reduced from the data to insights. The cycle time is greatly reduced. And not only that one, you'll be able to very quickly establish performance, baseline performance. So what I mean by that one is, so let's say you quickly run the algorithm, and let's say Bayesian is typically really fast, depending on the size of the data sets. And Bayesian algorithm will say, okay, my performance is 65%. So with the first algorithm that's already completed, you quickly get an understanding of what your baseline performance is. And sometimes if you're lucky, you can also get the upper limit. So in some industries, there are certain constraints posed on the solution. For example, in credit industry, according to one credit reporting agency, your output has to be monotonic with the input. So under these constraints, typically when you have constrained models, the performance of the models go down. But if you very quickly are able to establish the performance of a no constraint solution, you are already establishing the upper limit. So once you know the baseline and once you know the upper limit, you quickly know what is the performance that you can expect out of your solution that's going to come out. So as a consequence, the data scientist can focus a lot on deeply understanding the context of the problem, of how the solution will be used, and also translating this context into the model design. And finally, once the insights have come, take these insights and figure out a way to create value on a regular basis. So all this is good, but why does data science practice need data scientists as opposed to completely sufficient with AutoML? So here is the reason. Many times, the business context understanding cannot be automated. So let me give you a quick example. So let's say you have reached a stage where the problem, we know that we are going to generate a classification solution, right? Now, the next immediate concern is, how are we going to get the data? More often than not, you will not have labeled data. So the immediate question becomes, how am I going to generate labeled data? So one possibility is for the team to spend more time and generate labeled data, or to outsource the labeling to a third-party company such as Crowdflower or Mechanical Turk or companies like that, or use advanced techniques such as self-supervised learning or active learning and so on. So what is the right strategy is completely dependent on what kind of data it is, whether a normal person will be able to generate labels and so on. And another context that is really important is when you start with out-of-the-box solutions. So let me give you a specific example. Like a lot of us, almost all of us love open source solutions. So when we take this open source solution and you use and you train the algorithm using your data, you'll get a certain performance, then you can fine tune it a little bit and you can increase the performance. But there is limit to how much you can push the performance, because the open source tool was never developed for your specific domain. So the only way to get a really squeeze out the next level of performance from this solution would be to systematically inject domain knowledge into the algorithm. So let me give you two examples. So let's take search. An open source search engine such as Solar, Elasticsearch, they don't really have a notion of color or size or quantity or brand. So if you really want to enhance the e-commerce search engine, the search engine has to be aware of these concepts, and this knowledge has to be systematically injected into the search engine. Similarly, recommendation algorithms. So in a typical e-commerce setting, you have mainstream offerings, budget offerings, and you also have premium offerings. And there's also a notion of equivalent brands or competing brands. So your recommendation engines have to be aware of these facts, and these facts have to be injected carefully into the algorithm by a data scientist. So this is one aspect. Another aspect is lot of algorithms used in data science practice have very high runtime complexity, and this runtime complexity shoots up with the size of the data. So in a context of e-commerce recommendation engines, again, the runtime complexity is directly proportional to the number of products and also the number of transactions. So if you directly pump in all the data into your algorithm, it's waste of a lot of computations, because a lot of combinations don't make sense. So let me give you a very specific example. So let's say people are likely to cross shop for running shoes and activewear at the same time, but unlikely to buy toys at the same time. So it makes sense for the algorithm to analyze transactions that involve running shoes and activewear together and generate recommendations for these two categories together, and to process toys separately. So this way, only sensible subsets of data are processed at the same time. So how do you get this knowledge? First of all, people have to understand what so first of all, there has to be a clear understanding of time complexities, and also what partitioning makes sense. For example, sometimes it makes sense to divide the data based on your business units. So here is one example, the one that we just talked about, running shoes, activewear, and toys. Or maybe it's analyzing transactions at a particular time period, maybe a month, maybe a week. Or sometimes maybe it's analyzing transactions that belong to a particular geography, like maybe Northern America or South America or something like that, or some combinations of partitions, right? So you require an intimate understanding of the business and also the runtime complexities to pick the appropriate combinations. And another aspect that is also important and that requires deep understanding of the business is what kind of, how do you select models, right? Suppose if the solution, the model is being for internal analytics, so it doesn't really matter how long the algorithm takes to run. So let's say if your situation is such that you have two classes of data and you have very less samples in one class and the other class has so many samples. So something like a k-nearest neighbor algorithm would be a fantastic choice. But unfortunately, a k-nearest neighbor algorithm is not a good choice for real-time serving, because a nearest neighbor algorithm will generate a prototype in real time and then make a decision on top of it. Therefore, it's not suitable algorithm when you're expecting real-time response. So let me switch gears a little bit and argue from a different perspective as well. So classification is one of the most common data science tasks. So again, let's say we have a two-class classification. The simplest way to formulate this problem would be class 1 or class 2. But when we do this way, we are simply dividing the entire space into two classes. Now, the consequence of this one is that when you have a data point that does not belong to class 1 or class 2, your algorithm will be forced to put the data point in one of these two classes. And more often than not, there's also another situation where, though it looks like a two-class classification, it's not really two-class classification. So imagine, again, trying to determine fraud. So it is conceivable to think that, okay, all we have to do is to examine every transaction, then make a decision if it is fraud or not fraud. But in reality, what we want to do is the algorithm to catch fraud and pretty much ignore everything else. So here, the architecture that makes sense is like, or the formulation that makes sense, it's actually a one-class classification. We want to focus only on fraudulent class. So this way, the representation used to represent fraud and non-fraud need not be same. It can have grossly different representation. Whereas in a two-class formulation, you are using similar kind of representation to model both classes. And sometimes that may or may not be successful. Another way to formulate a two-class classification would be two one-class classification problems. So why is this important? Is because let's say our requirement is to specifically tune the precision recall characteristics of our solution. And also we have a requirement that we want to explicitly handle cases that do not belong to any like class 1 and class 2, right? So this happens many times. Suppose if there is a problem upstream in the data generation, or maybe a new kind of data showed up, we want our algorithm to say that, yep, this is completely new data. I've never seen it. Please handle it. Okay. And also, there are several design choices that one has to make in a successful solution development. So rarely in data science practice, a solution is composed of just one algorithm. It's actually composed of many algorithms. So how do you assemble these sub-algorithms into a solution? Completely depends on understanding what you're trying to accomplish. So let's say in one particular way, you're trying to, like in one particular requirement, you are trying to reduce the work. So what this means is you have a bunch of data and you want machine to process as many data points as possible and leave the hard cases for human beings. Okay. So one example would be, I want to route my customer service calls. When I call a company, so the automated system will try to figure out, oh, is this customer having issues with account setup? Well, if that is the case, let me route it this way. Or is this customer having problem with their signal? Or is this customer having problem with their bill? So the algorithm will process all the cases that are very easy for it to process, and then route everything else to human beings. Another kind of use case is that we want the algorithm to filter the work for human beings. So again, let me reuse fraud example. So let's say we have 100,000 or a million fraudulent million transactions in a typical day, and we expect, say, 50 fraudulent transactions in a typical day. So, and we only have limited number of humans who will be able to process those fraudulent transactions. So in this case, what we want the algorithm to do, or the solution to do, is to filter out vast majority of those normal transactions and only capture a small set of transactions that cover pretty much every fraudulent transaction that's going on, right? So imagine out of this 1 million transactions, capture maybe 100 transactions that contain 50 fraudulent. So here humans, for every 2 cases that humans process, one of them will be a fraudulent transaction. So that is one design. The third design, this is mostly used for non-mission critical applications, is when we don't expect any human beings to be involved in the solution at all. So what we do is we train a bunch of algorithms, and we train another decision system that would take the decision from all of these individual algorithms and assemble into one final decision and resolve the data. So this is another requirement. So what is the architecture to combine these sub-solutions to the final solution is not trivial. It requires deep understanding of what you're trying to accomplish. It's unlikely that an AutoML software will have these kind of abilities. So there are other aspects as well. So let's say, again, let me use the fraud example again. Suppose if a person who does not have data science background is training a solution to process fraudulent transactions, and let's say if they're optimizing it using accuracy as their metric. Now here is the problem. All the algorithm has to say is that there is no fraud at all, and the algorithm will still be 99.99% accurate. Now this is completely useless, because all the algorithm is saying is there is no fraud at all. So what we really want is a solution that has been optimized for high precision and high recall for the fraud class. And it need not optimize the entire solution, like for both for fraud and non-fraud, because non-fraud is not interesting. It's not interesting to us. It's only fraud is interesting to us. So having it, you need data science training to select appropriate metrics. Then let's say another, like lately with all the compliance requirements and like companies trying to design ethical AI, one of the questions that we want to answer is what is the source of bias? So they look at the model and the algorithm is behaving or the solution seems to be behaving in a particular way. So we want to find out what happened. Where did the bias come from? Did the bias come from the data? Did the bias come from the modeling? Or did the bias come from interpretation of the results? So what's happening? Or if you take something like Apple, somebody like Apple. So Apple products are mostly premium products, and not everybody in the country is expected to buy them. So those products are targeted to a particular audience. So here your entire business operates in a particular bias segment of the population. So you need a data scientist to completely tell where the bias is coming from and then handle it appropriately. And another one is, how do you select right algorithms as the data scales? So let me give you an example where, suppose if you want to run a hierarchical clustering for entire US population or something along entire US population, let's say it's for 200 million people. If you want to run this algorithm for 200 million people, this algorithm would cost you 40 quintillion computations. So no matter how fancy your cluster is, 40 quintillion computations is a lot of computations. And this would tie up your cluster for a year or more than a year, depending on the configuration of your cluster. Okay. So what we want is the results to be processed that look like hierarchical clustering, but using cheaper algorithms. So this requires intimate understanding of the time complexities and what's actually expected out of the solution. Then the final point that I'm going to talk about today is when the business comes back and says, you know what, I really don't like this solution. Let's improve it. So how should it be improved? Should we change the formulation? Should we change the model? Should we change the data? Should we change the interpretation? So in AutoML or an automated software, it's very unlikely to help you that way in situations like this. So with these diverse set of arguments, hopefully I'm able to convince here today that data science practice is fairly broad discipline. It requires deeply understanding the business context and translating the context into solution design. And as of today, AutoML is akin to a exoskeleton. right? What I mean by that one is you can rarely use an exoskeleton by itself. However, when you give it to somebody who knows how to wield an exoskeleton properly, you're going to greatly amplify the power of that person. So here in this case, if you give AutoML to a data scientist, they will end up becoming much more productive. Okay. So with this, I'm going to answer the question that I posed in the beginning of this talk, that AutoML is not a panacea for data science talent shortages. With this, thank you very much and have a great rest of the day.